Hi, good morning, everyone. So I am going to talk about this precision measurement of hyperfine structure in cesium, this 7D states. Uh, this kind of precision measurement is important in particular in cesium because of several reasons. Like we can study, okay, so we can study the parity non-conservation experiment in atomic systems, and cesium is a good candidate for studies this kind of experiments. The reason is cesium has very high atomic number Z, and this parity non-conservation experiment sensitivity is scales with Z. If we have high Z, then the sensitivity is higher. Also, this cesium has very precise atomic structure calculations. So, in this experiment, what they done is that this 6s to 7s transition in cesium, this is highly forbidden. So, if there is some parity non-conservation present, then that mixes this 6s states to the p states, and that enables to transition from 6s to 7 states. So, if we can detect this transition in the experiment, then we can say there is this parity violations. Uh, also, in my case, the transition is not H to S, this is H to D. But this H to D transition is also important because we need to check all the other theory that whether that's explained my whatever I'm getting in the experiment is correctly or not. So also the hyperfine measurements and gives information about the nucleus because this hyperfine structure arises because of interaction of electron magnetic field with the nucleus. So this is the energy level structure of this cesium, and this is the hyperfine their hyperfine structure. This excited 7D state and ground 6s states. So this H to S transition is not dipole allowed by single photon. So we use two photon transition. The cesium atom absorb two photons of wavelength around 767 nanometer and get excited to these 7D states. Then it decay back to this ground state by emission of fluorescence. So we detect the fluorescence at 672.5 nanometer for this 7D3 half excited state and 697.5 for 7D5 half excited states. And from the fluorescence we observe the spectrum. In the all earlier measurements, so what they done, they instead of detecting this 672.5 nanometer, so they detect some another fluorescence which is at 450.5 nanometer. But this emitting fluorescence is those cesium emitters which are in the ground state, they can again absorb this fluorescence, so their signal strength that they will detect that will be smaller. So for that, in our case, the signal to noise ratio for our spectrum will be much better as compared to this one. And also we have this much better statistical uncertainty in our measurement as compared to all the other earlier measurements. So to before going to the experimental details, just to compare the Hyperfine coupling constants, which is this A and B, this is related to the magnetic dipole moment and electric quadrupole moment of the nucleus. So these are the value that we have measured. So and these are the all earlier measurement. The last one is the theoretically calculated values. So you can see the statistical uncertainty for our case is much small as compared to all the other earlier measurements. So if we just send a laser beam to a cesium vapor cell and scan its frequency around the resonance, then cesium atom can absorb two photons from this same beam, and this will give a Doppler Borden spectrum like this. But we are only interested in this hyperfine region. So, but as you can see, this hyperfine signal strength is very small as compared to this Doppler background. So so we use this counter propagating beam that just cancel the Doppler effect in the first order. And this is the schematic of my experimental setup. So we use external cavity diode laser of wavelength around 767 nanometer. So we can directly scan the laser frequency around the resonance by changing the cavity length, but that scan of frequency will be very nonlinear. So instead, we use this acoustic optic modulator. So we divided our laser beam into two parts and sent one beam to this AOM2. And in this AOM, we apply RF from 90 to 126 megahertz, and that's change our laser frequency. So with changing this laser frequency, this AM doing two more things. It's deflecting the laser beam from its initial propagation direction, also it's reducing this power of this laser beam, and both this deflection and the power reduction is not equal for all RF frequency, and these two are not acceptable for our measurement. So to compensate this deflection, we use the cat's eye retroreflection configuration using this lens and the mirror, and to stabilize the laser power. So after this laser, this beam coming from this double pass AM configuration, we pick up some of this beam and give say input as one of our electronics feedback circuit, and that feedback circuit actually control the RF power that we are giving to this AM, and that stabilize the laser power. This green one is the laser power coming from this double pass without this electronics feedback, and this orange one is the with this feedback circuit on. So then we send this laser beam to a cesium vapor cell and reflect it back for counter propagation, and we also focus the laser beam that increase the intensity, and this will enhance our signal strength. So we keep our cesium cell inside two layers of magnetic seal that reduce the external fields to around 2 milligauss, and then we collect the fluorescence in this PMT, and we observe our spectrum in oscilloscope. So and during my experiment, the ECDL frequency can drift, and that will introduce nonlinearity. So to stabilize it, we made a similar setup with this AM1, and we detect the fluorescence here. And this from this fluorescence signal, we're giving a feedback to this laser system, and that stabilize the laser frequency to one of this hyperfine transition. So with this, we locked our laser to one of the hyperfine transition and scan the AM2 with around the resonance and then get the fluorescence spectrum. And from the oscilloscope, we record the sample spectrum as well as we average it in 4 times and 16 times in the oscilloscope, and then record the spectrum. And this is how our spectrums look like. So this is for 73 half excited states. We locked our laser to F'4 transition. This is for F3 to F'2345, and this is for F4 to F'2345. And for similarly, we did the same thing for 75 of excited states. We locked our laser to F'3 excited state, and this is the spectrum we are getting. This is for F3 to F'12345. This is from F4 to 23456. And all these 4 spectrum that I have shown, these are the average 16 spectrum. So, and this is how our sample spectrum look like. So next we feed this spectrum with a Lorentzian function, and this is the fitting we are getting. So you can see this fitting is actually quite good, but in this region there is a little bit discrepancy between our measured data and the fitted curve. So next we try to fit this with a void function, and that's giving a little bit better fitting as compared to the Lorentzian. So we continue to use void as our fitting function, and whether we are using void or Lorentzian, this absolute peak positions remains unchanged. So there will be no effect on the peak separations. So from this void fitting, we are getting their absolute peak position, their line width of each of these transitions, and this amplitude of each of these transition. And by taking the difference between these absolute peak positions, we are getting the peak separation between this hyperfine, different hyperfine levels. So this is for 73 half excited state, and these values we are getting for F3 ground states to excited 73 half, and this is from the F4 ground states. And this all these data points are actually average of 7 different spectrum. So and this you can see there is a little bit discrepancy between the F3 this peak separation that we are getting from the F3 spectrum and F4 for this F'3 and 2 peak separations, but we don't really clearly understand why there is a difference. So for this is for the 75 of excited states, and here we also did the similar thing, and we are and this black point and each of the subplots, this is the average of all these values. So next we compare our results with all the earlier measurements, and these errors are only the statistical errors. So these are our measurement, and this is the earlier measurement. So we can see that these statistical errors in our case like 5-6 kilohertz, which is at least around 20 times better than all the earlier measurements. And these are the values we are obtained for this 75 of excited states. And this for this also our statistical error bars are much smaller. And this for this f prime 2 and 1 separation, and there are no earlier reported values, and we are the first one to report any values for these separations. So next we check the systematics effect. So whether that's like this intensity or the temperature has any effect on this peak separation. So we record our spectrum at different laser powers for several days. This is at high power to low power, and we repeat for like several days, and we don't see any significant change in the peak separation within our error bars. This is for 73 of excited states, and this similarly we have seen the similar laser for the 75 of excited states. Here also we don't see any very big change in the peak separations. So, but what we observe is the absolute position of each of these transition is changes as we change the laser power, and we are expecting that this shift should be linear because it is start shift. This will be linear in power. So we fit each of these peak separations with the power with this laser power within linear fit, and these are the result I am getting. So, and this is also true for 75 of excited states. And this is the first direct observation of start shift for the 75 of excited states. And these slopes on each of these figures are like almost equal, and that's why you don't see any change in the peak separations for as we increase the laser power. So but for this peak separation, this does not have any effect. But if someone wants to measure the absolute frequency, then they need to take care of this start shift. So, and this is the line width of each of these transition as we change the laser power. So we have to check whether that is changing, but there is no such significant change in the line width. Okay, so next thing we study is that we change the temperature of our cesium shell. So to check whether the temperature has an effect on the peak separations. But within our error bars, there is no such big change in the peak separation. Beyond this 150 degrees C, there is a little bit change, but we are quite below that point. So this temperature effect is also taken care of. So, but in this temperature case also, we see that absolute positions of this each of this hyperfine transition changes as we change the temperature, and this is how they change. This is for this F4, this 3 half excited state, and this is for the 5 half excited states. Okay, so as we increase the temperature, we observe that this line width of each of these hyperfine transitions increases. So, and this is in log scale. I plotted against the vapor pressure. From the theory, we are expecting that this line width should increase linearly with the vapor pressure, and this figure we this blue curve is the fitting linear fit to this observed line width, and this is the fitted parameter that I have got. Okay, so in overall, so in our measurement, the statistical uncertainty is around 10 kilohertz. So we are using the counter propagating beam, so that cancel the Doppler effect in the first order. But in the second order, we can have a Doppler effect around 0.449 kilohertz. So, and we are using the magnetic shielding that reduces the external magnetic field to around 2 milligauss. So the maximum shift in the peak separation can be around this 8 kilohertz, and the start shift that can be gives a maximum uncertainty of around 4 kilohertz, and the temperature shift can gives a around 10 kilohertz. So including all the systematics and the statistical error, and this figure is showing that the comparison of our values with this all the earlier measurements. So our error bars are so small that you cannot even see here. So it's at least like 10 times better than all the earlier measurements. So in summary, so we have measured this hyperfine structure of the 70 states with a better statistical precision as well as systematics. So we directly observe the start shift for each of these transitions, and which was not observed before. We see that there is a collisional shift in the peak position, but there is no such effect on the peak separations. and including all these systematics and the random error. So this our measurements are around 10 times better than earlier measurements. So I'd like to thank Sourav Dutta for guiding me during this entire experiment, and Gorachand Tats, he helped me during the experiments. So thank you.
Thank you, Bubai. Any questions?
On this Stark shift measurement, did you extract a polarizability value?
No, I have not yet extracted the polarizability yet. I just see how much it change if I change the intensity.
Do you know how much the uncertainty it may have?
This is the fitting uncertainty.
Statistical and other uncertainties you have not considered.
Not yet calculated, but I will.
Because that will be very interesting. Then that will be more interesting than hyperfine structure constant study.
Shubhadev, the thing is, you had asked a question. So you can actually measure center line positions much better than the line. And if you lock the laser, and so we are not scanning the laser, and you can scan 150 kilohertz probably, most likely 150 kilohertz, 150 to 200. We have not measured, but it's not less than that. But it doesn't. You are not never limited by line width of the laser when you do spectroscopy. You can, when you average, it all boils down to signal to noise ratio. You can have a very broad laser, but you can still measure the center peak position with, depending on if you have signal to noise ratio of 1000, you can split the line into 1000. So the line width will not come into the picture. And in fact, in this case, if you repeat the measurement on the scope, you will not see that it is refreshing. I mean, it's so stable that if it was 100 kilohertz, you will see it jittering. Here, you will not even know that it has sort of refreshed because the scan is completely phase stable. I mean, it's true anyway.
Thank you, Sourav.
Hi, can you?
There are two more questions.
Yeah. So the expression you showed in the beginning for the hyperfine levels, if you go back to that expression. Yes, no, yeah, I have some questions. See, this is not exact. Okay, so you must have fit your data to this equation. And what you're claiming, your precision is very, like high. So now I would expect that the second order, induced second order hyperfine correction coming from dipole-dipole interaction could be of same order for this transition. I'm not expecting that there will be significant contributions from octuple transition, octuple moment, but from the dipole-dipole interaction. That could be significant. That you should consider.
Thank you.
Hi, Bubai. Bubai, go to the next picture. So there is a power stabilization graph is there.
Yes.
Yeah. So this is the power of what? This blue curve. It's
Okay.
and
So this is the power of the laser beam that is coming from this double pass. That is this beam.
no. Basically, this variation is coming from is quite a lot. Like and how? What is the stabilization scheme here? How the down one is the stabilization, right? After.
Yes.
So how do you do that? That much variation.
Okay. So we take some laser beam from here and give this detect that power like little bit in the photodetector, and that way give us a input of our frequency feedback loop, like, and this feedback loop control that RF input that is we are giving to this AOM. If we give more RF power to the AOM, then this transfer efficiency of this AOM will be large. So, and this circuit controls that what should be the RF input that we will give to this AOM. There is a voltage control attenuator.
Yeah, Bubai, great talk. So regarding this experimental layout that you have shown here, can you just naive question, how do you do this frequency conversion from, like you are presenting on the x-axis, you're showing the plots where you have the time on the x-axis versus the fluorescence, but your actual measurements are with respect to frequency. So how do you do this conversion from time to frequency?
We are applying a linear ramp of 1 Hertz in this OM to scan the frequency.
Okay.
And we precisely know that within 0.5 seconds, it's scanning around 36 megahertz.
Okay.
It's my scaling factor.
Okay.
Time to frequency.
from that you are doing the scaling. Acha, okay, okay. And the other question is related to what Bijayda asked regarding this hyperfine coefficients A and B. Do you have any further plans to incorporate some, let's say, modification in the experimental strategy so that you can refine the measurements for A and B like you have obtained from this work?
Right now, like maybe we can try it in like instead of vapor cell in cold.
Acha,
Cesium
so
sample.
so you're hoping that if you do it in cold atoms, probably you will get a better result.
Because
for-
maybe if there are some collisional effect, because
Mhm.
increasing the temperature
Right.
to have higher number densities, so that problem not will be there.
Okay. Okay. Fine. That's all. Thanks.
So actually, I have a question in continuation with Arijit's frequency calibration. So you said that you have 46 megahertz per second.
36 megahertz.
Yeah. So that, how do you cross calibrate? Means, how do you know that this is not 36.5?
It's checked in the spectrum analyzer.
Okay. So you are relying on the spectrum analyzer clock. All right. Okay. Thank you. Fair enough. Okay. If there are no more questions, then let's thank Bubai again for this nice talk.